Welcome everybody to our last session of the seminar. Today Daniel will give the first talk and the second one is for Héctor. So thank you, Daniel.
Okay. Thanks, Luis. So thanks to come here to continue the torture, the torturation, how you say it? Para continuar la tortura that we are doing with Héctor, but no, it is a lot. We were all the semester doing this, so it's good that we finished together because, yeah. Okay. Maybe I'm not sure. You were following the workshop in UK, something related with this, so will be not. So we're okay. So let me. So the goal of always is. So with Chuck is so much. It's different. Tomorrow you need to give a token with Chuck, so you need to practice a bit. This is Heidegger. Hida theory, no? For modular curves. So that is the title of more or less the paper, no? So the talks that we had 4 talks. So the first one was me, and there was Héctor, me, and Héctor. So the first one was what I did is the statement, no? Kind of. Then Héctor explained the mod P theory. So that was the last week, and today we will end the construction of the proof of what we state, and that will be firstly I will try to speak about big modular shapes. They are huge shapes that in some way that interpol the other one that we were interested here. You remember this W, omega k, and then Héctor will explain the construction, no? the proof, more or less, of the theorem. That is the proof, the construction. So that is more or less the goals that we had, and so I will explain my talk today. So this is part 3, no? And so big shift, no? I would just start recalling a little bit which is our motivation, no? And then I will introduce 2 ingredients that will allow us to perform our goals. So we will try to be on I start at 10:10, we can say so. Hola, Juan Pablo. I can finish at till 11. Okay. Okay, which is the goal of this we are doing? Okay, so remember that we have our main role is played by this is a modular curve. Modular curve of gamma 1 and level. Okay, that is what we introduced last time. So here you have 2 numbers, p is prime, n is bigger or equal than 3, which is coprime to n. This is the data that we have behind. Then this is a modular curve of level gamma 1, and that was the main geometrical player that we are interested, no? Okay, so where is our goal? Our goal is to Okay, to interpolate. Let's be precise. To interpolate H0 of x wk omega k, which is this is the modular shift, no? And H1 x wk when k, this is the interpolation means you are varying something, okay? So you are varying k between the integers such that you are moving this p-adically, no? when chi moves p-adically. Okay, that is our goal. So to be more precisely, so what's here is higher HIDA theory. That means something behind is HIDA considered in the middle of the 80s, I think, the ordinary part of the cohomology. So we will more precisely we care about. So remember that we have this operator TP acting on the cohomology, okay? So this TP acts in both spaces, which are ZP models, and then you can ZP is nice, and we can apply the theory explained by Luis. So that exists the projection, operator projection. So you look at the image of this. Okay, I equal 0 and 1. This is the image of the operator acting on the cohomology. This is called the ordinary part, okay? So this is the ordinary part of the cohomology. Okay, so we care about that. So by the way, so if you change Coleman, if you change HIDA by Coleman in the 90s, he tried to do the same but considering more general spaces, okay? But okay, we just care about the ordinary part, this part of course. So the strategy is like, well, strategy will be, okay, so you want to put in families, so to construct a big model, interpolating these ZP models. So all these are ZP models, okay? Okay, you're really ZP model. There is no geometry behind. So the construction is geometric, but the object is the ZP model, okay? So the strategy is to go more deep and to interpolate the objects behind them, the chiefs, okay? So you will construct a big chief over some geometrical object, interpolating them, okay? So strategy, interpolate the chiefs. The chiefs omega k, with k vary here. So the idea is very weird because you need to, these are line bundles, invertible chiefs over the modular curve. So what you will try to do is to produce some big chief, interpolating them. So from that the name big chiefs, okay? What I am going to do now is to explain the construction of these chiefs. And then Héctor will use them to prove the main theorem. So that is the strategy, okay? So that is the intro. So the two ingredients that we need here. So to perform this construction, we need two ingredients. So the first one is so as we are constructing chips, so everything will be very geometrical now, okay? So I will use some language that maybe is not very familiar with you, but it's good that you know that there exists, and maybe you can check in books. And okay. So firstly, you need to take what you do. You take the modular curve. The modular curve is a scheme. So schemes are locally rings, no? So when you have a ring, you can do a completion. You can complete this to respect to some ideal. So you can take the p-adic completion. You can complete with respect to the p times the ring, and that produce given a ring, you produce a p-adic completion of him. Gluing them, you have the same procedure for schemes. In fact, so we will call with these matfrak letters, okay, the p-adic completion of X, okay. So this is very standard. Oh, and that is finally okay. So you can p-adic complete an scheme now, which is the same to p-adic complete rings but glue them. Okay. So you have this scheme now, and you can look at the. You have ORD here, which is the ordinary locus of this scheme. Okay. Okay, so the ordinary locus, what it means is, so you remember that the modular curve parameterizes elliptic curves. Okay, so you look just the part of the modular curve which parameterize elliptic curves which are ordinary in the language of Héctor. I think maybe Héctor defined ordinary over finite fields, maybe, no? But the definition over ZP, for example, is that when you take mod P, the elliptic curve is ordinary. Okay, so that you call ordinary over ZP. Ordinary, you remember, ordinary is like elliptic curves over FP, for example, that when you look at the torsion points over the FP bar, it's just Z over PZ, not square, in non-zero, okay? You cannot be in square, you cannot, yeah. In an FP vector space of dimension 1. That is ordinary. So you have points. Okay. Okay, so that is the first ingredient that I wanted to introduce. And the second one is something that is familiar with you because it's, so you take the Iwasawa algebra. Okay. So firstly, we need a geometry. So this is very geometrical, no? So we need some geometrical object over which we will work. So we care about this one. Okay. So maybe just to recall something. These two spaces, in fact, are formal schemes. So there is a theory that formal scheme you can. Maybe Javier is reading a lot of this algebra geometry. You know. Okay. Okay. So we have this formal scheme. So this one is we will be more interested to perform the construction. There the stuff works well. So this is the geometrical object. So we need still the idea of to construct something big, no? To put K in families. So that is performed by the Iwasawa algebra, as we discussed last time. We have here this ideal. Yeah, it's not a maximal ideal. It's a Jacobson radical. Okay, and okay, this intersection of all the maximal ideals. Okay, and this, with respect to this one, it is complete Noetherian, and yeah, have very good. Is profinite. So you can apply again for models over this one, the theory explained by Luis. Okay, the second ingredient that I want to give I need is the idea of weight to be big weights also. So the universal weight is the following way. So we will call this K un. Okay, and that goes from ZP star to lambda star, which is just you take an element here and you need to look this element inside here. So the natural way is to look this as here, no? Not here. Here is a good way to look at them. So you look at this, I will call in bracket them because to mean that is here, okay? Okay, that is the universal weight that gives you the idea to put all the weights together. Okay. So just a remark. For all K in Z, we have the following. So take ZP star, take the universal weight, and you go to lambda star, and then you go to here. Okay, so here is the universal weight. You just do that. Okay, so here last week I introduced a map was called the specialization in k. You remember? It was to take z power k. So you do exactly that. Okay, so if you look at the composition of these two maps, it's just z to power z to z to power k for any k in the integer. So that is this universal weight gives you the idea to recollect all these classical weights, which are these numbers, together. Okay, this is the universal weight. Okay, okay, now I already introduced the two ingredients. So now let's perform the construction. Okay, the big chiefs. So maybe you will be a little bit confused in some part, but this is fine, okay? Just try to follow the structure of the construction and how we will use them. Just by, yeah?
Are there many stars in some point?
Too many stars?
Algebra,
This map is a homomorphism of algebras, yes, but
so it's not algebra because it's stars. It's a group.
now without the stars, it's a homomorphism. Oh. Ah, this is better.
Yeah.
Okay. Yeah, without the stars, it's a morphism of ZP algebras.
But this guy is not an algebra.
Yeah, but when you put stars, it's a morphism of the unit of the algebra. Yeah, any morphism between rings induce a map between the units of the rings. No? Okay. Okay, the big chiefs. Let's start with the construction now. Okay. 15 minutes. Okay. Okay, so the construction. Okay, so. Oh, it's good. Okay, we start with the universal object over the ordinary locus. You have also an ordinary object, so you use this. Then what do you do? So you look at the Pn torsion of this. Here. Oh, this shock is much better. No? This is a finite group scheme over this formal scheme. Okay. Here is something that you just try to believe. Or maybe just to remark a little bit. So when you are ordinary, you have something called a canonical subgroup, which is something just stated in this way. There exists a subgroup of rank Pn. Okay, so it's half of the size of this group. No, this is size P and P2n. No, and this is half of the size, and these have very nice properties. But I'm saying nothing. No? With nice properties. So which properties? Maybe these properties that I will say are not very precise, but so maybe some properties is that this is a multiplicative group, no? So locally is mu the Pn units, okay? So locally is this, and one important property is that. Okay, see this canonical subgroup, there exists for each n only in the ordinary locus. Why? Because the elliptic curves are ordinary. And you have, when you look at them mod p, you have a precise piece of size p power n. So the Pn torsion is p power n size, okay? Okay, so this mod p should be related with this stuff, and so mod p is related in fact to Frobenius, okay? In fact, mod P, I think we say that is the kernel of Frobenius, no? Yeah? Okay. So this is the canonical subgroup, which is very important. In fact, the higher Coleman theory follow the same steps and modifying a little bit this part. The rest is almost the same, but you need to modify a little bit this part. Okay?
Can I ask something?
Yeah?
Locally it's what?
The group of Pn root of the unity.
Oh,
Okay. What you say?
It's a mu. It's like a u.
It's mu, yeah. Oh, mu maybe?
I think it's the other leg.
Yeah. Yeah, it's great. Oh, sorry. Yeah, you
I
look.
didn't recognize that. I'm not trying to be difficult.
It's interesting because you recognize the subtleties for us. Okay. Okay, that was the first object that we need. So the second one, let's put a definition here. We consider these have fancy names. It's the Cartier dual. The Cartier dual is of this group is the dual, no? So we take the canonical subgroup, we take which is the dual. The dual will be the homomorphism, yeah? The homomorphism. So when you have a vector spacer, the dual of the dual is the homomorphism from the space to the constant you are working on. So here will be this. Okay, that is the Cartier dual. Okay. Okay, there is a group scheme over. So I want just to remark that everything here is over this object. Is the ordinary locus. We are doing everything. Okay, so that is a. We produce this new group scheme over the ordinary locus. What we do now? Okay, so then you have that. You consider another. It just is I put definition that to organize the name, but it's just a construction, as you see. Construction. You have the p-n torsion. You have the canonical subgroup. You have the dual of this, and now you put all these groups together, and this is called the Tate model. No? The Tate model of the canonical group is the common notation is to use something like that. We're taking the Tate dual of the dual, no? The Tate module of the dual of the canonical subgroup, so it's the inverse limit of these groups. Okay, one observation that these are the relation between the canonical group of ledger n is included in the one with ledger n plus 1. When you take duals, the arrows go in the opposite direction. You have a map from n plus 1 to n. So that makes sense, this limit, okay? Okay, so what we perform at the end is, so you put all these finite group schemes over the ordinary locus, you put together in a big stuff, and now this is something that is achieved. It's really achieved, but in the following side. In this side, so you take. So everything is over this stuff, no? We are everything doing over the ordinary locus, and we put all together all these groups. So now that is really achieved in the Pro et al. Site. Okay. This site was constructed by Scholz in 2012, and then improved by him and Bath and a lot of people. And that was exact. So before Scholze, this was just a pro chief, inverse limit of chief that doesn't exist in the category or in the tal side, okay? Was a pro object. But with the pro et al side, this is really a chief, okay? It's really, really a chief, okay? What's more, this Tate model is locally isomorphic to ZP. Locally in this topology, in the pro et al side, okay? This is, okay? Okay, so now we have several steps. We have the universal object, the p-n torsion, the canonical subgroup, the dual, the Tate model, and now one more step. Maybe I should write a map here. Oh, I have no. Oh, buena. ¿Ah? Oh, gracias. ¿Tenía un plumón? Ya, pues, vale. ¿Tenía? Okay, let's just, while the plumón, the USACH tower is the following. So now we are in a new level, and we will take the trivialization of this object over the curve. Oh, you have plumón? Okay. ¿Tenéis plumón ahí?
Ese rojo.
¿Está bien? ¿Está rojo? Entonces, vale. Oh, acá. Está funcionando mejor. Entonces, una especie de mapa de la construcción para que no nos perdamos. Entonces, empezamos primero con el objeto universal, ¿no? ¿Qué pasó? Ah, ¿está hablando español? Ah. Oh, sorry. So you start with that, and you take the p-n torsion, and you consider the canonical subgroup here, and then you take the the dual, no? You take the Cartier dual, then you take the Tate model. We are in this moment, no? We are here, okay? And now what do you do? This is locally ZP, so you take global you take all the trivialization of this stuff. So you take, and that is the USACH tower. The USACH tower will be the trivializations of this Tate model. Okay. Oh, we are closer to the construction. So the construction is a little bit involved, as you see, but it's standard. This will, okay. At the end, I will do some remarks, but about the construction in general. So what is this? This is it was a tower. It's a tower over the ordinary locus. So this is a scheme over the ordinary locus. So there is, okay. Oops. So you have a structural map from here. Okay, it's a tower because it's something over this one, and this distance is very big. Okay. In fact, it's a formal scheme. This is a profinite et al. Cover. Okay, it's not a finite et al. It's profinite et al. Okay. In fact, there is a Galois group acting here, which is Z P star. So you can construct this in another way using modular curves of level at P. You add more level at P, and you can construct this. Okay, so now we are done. Finally, one more remark. We will perform the following construction. So you take the the functions over this scheme take the push forward of this one. So now it's a shift over this curve. Okay, so this is a ZP model. You can tensor with lambda. So you are mixing everything, you see. So this is very geometrical. Okay, it's a huge construct. The size of this tower is ZP star. Okay, and you are making it bigger, taking this big model too. So you are doing it two times bigger. Okay, but you do that. Then here, because this tower have ZP star as a Galois group, you have an action of ZP star. Okay, here you have an action of ZP star. It is just the universal weight, no? So you take an element here, you take the image here, as we defined before. So you have an action in both sides of ZP star. And what you do finally, and that is the end of the construction. What you do at the end is the following. So definition. I will put just a name for this talk. It's not official. The big modular sheaf is the following. So what you do, we will call this. It's the same as suggestive notation. To say that you are in one sheaf, you are having all the weights together, okay? And you are taking the omega power this big weight. And what is the definition? It's just take the ZP invariant of this one. Okay. Okay. So you take this object. And you take the ZP star invariant of this. Okay, that is the big modular shift. I know the construction is a little bit involved, but what can I say? So this construction is over the modular curve. Maybe you think this is a little bit involved, but the same construction, so with the natural modifications, work for more general Shimura varieties. Okay, so it was, yeah. So it's a little bit involved, but works in general. So it's kind of the first step, some general stuff. So it's important. Okay, so let's just finish the recalling. So we were here, then we construct the Gusa tower, and then finally we take the invariant of the functions. No? Okay, so that is the construction. So it just states the main, maybe on time. Okay. Okay, maybe I will give less stuff that I had expected, but okay. So just some properties of this sheaf because it's important. So I will write this as a proposition. So firstly, this sheaf. So just to remember, it's a sheaf. Just shift over this curve, okay? It's a shift there. But now I will give more details about this shift. So it's an invertible. So you have it's not coherent because it's big, you know? Coherent shifts are of size of as this, the structural shift, or powers of this one. That is the main idea, no? This is not invertible as a here, but it's invertible when you look it's as a shift over this one. So as a model over this shift, okay? It's invertible over this one. Moreover, so what we were doing is to try to relate with the modular shifts, and the name is a big modular shift, so there is a relation with modular shifts. But if you look at the construction here, there is no omega involved. Okay, but in any case, there exists a canonical isomorphism for each k in z. I need to put that before. Okay, for each k in z, there exists a canonical isomorphism between the modular sheaf and this big sheaf when you make it smaller. So that means you take the specialization of this, no? Well, it's right here. So you take this one. What you do is to make it smaller, you need to take tensor with zp over lambda or the specialization with respect to the specialization. Okay, so that is the proposition. So what is saying this proposition that this sheaf had good properties and it's related with the omega. So which is the connection with the omega is behind this stuff. Okay, this is the Hoche-Tate map. It's very important in the theory, but I have no time to explain this. But the Hoche-Tate map gives you an isomorphism between this tensor something with the omega that we care about it. And that is key in the proof of this. Okay. Okay. So these are the big shifts that we are interested that Héctor will use. Okay. So now I will construct from this shift the models that Héctor will take care. Okay. So let's write this. Where's this nice chalk that I? Oh, here. Okay, so 3.3 big models, big lambda models. Okay. So let's insist again that here it was very geometrical. That was shifts that you were considering. Okay. Now we will take. So we care about the H0 and H1. That is our main motivation to interpolate when k vary. So naturally, for H0, we will consider H0 of this one. No? Seems very natural. Take the H0 of this, the global section of this huge model that we consider here. And this one works well because you look at this relation, so you are interpolating in some way the section on the ordinary locus of omega k. But Héctor will explain how you relate this with the section over all the curves, not just the ordinary locus. Okay. But for H1, so this is good, no? For H1, you can consider this. It looks very natural. Okay, that is what we will consider. And that doesn't work because it's 0. Okay? So this is bad. So the idea of this Boxer-Peloni, if I understand well, to solve this stuff is to take cohomology with supports. I'm not sure if you remember the talk given by Andy Graham during this last semester in this hybrid stuff. He used higher Coleman theory with the analog of this one. And there was some problem related with that, but he considered also not compact support cohomology, but cohomology with support in some closed spaces. And that is the idea, so the same idea works in general for other Shimura curves, it seems. So you need to stratify to take a stratification of your Shimura variety and consider very good, so well-chosen cohomologies, not the full one. Okay, so we need to modify this, so I will just introduce which is the model that we will use, okay? So the good H1, so good H1, okay? So that was bad, so let's introduce the good one, okay? For this, we'll need some notation, so, okay. So maybe here I will be a little, so the construction is very similar to what Héctor did last time. You remember he considered H1C and we had a discussion with Ariel, no? So the construction will be the same steps. So let's introduce some notations. Notation, you take n, an integer, a positive integer, and you consider xn will be x. So I'm saying in a very fancy way what you can consider just as a this is just x mod pn. Okay, I'm just writing in a very fancy way. So this is what we care. Okay, inside this we will consider the ordinary locus as before, no? Okay, so this I need just that, I think. Yeah. Okay, definition. So here we will suffer a little bit again, but is very close to Louis' construction. Firstly, okay, so we will consider H1C. This is what we are defining. So this is the definition. Okay, so this is the object that we are. The colors that have no meaning. Let's red to introduce something new. Okay, that I'm introducing this. So the definition will be a bit involved, but just start the definition by this will be the limit, the inverse limit of H1CXN, I think ORD here, ORD with coefficients here. So now I need to introduce this, no? This was not introduced, so I will introduce this. But the way to introduce this is very similar to what Héctor did. So let's go there. Okay, so what I need to introduce is this, no? H1C X and ORD of this. Okay, so what is that? That is a new limit. Is the limit of L now, so N was the variable there. So now we fix N and we move L of H1 Xn. Okay. So now still I need to explain what is J and F. Okay? Okay, let's go. But at this point it's very similar to what Héctor did. Because if you remember, that was Héctor, the N was 1 in Héctor's talk. And this, there was minus N times SS. And there was this discussion about Poulon zeros, no? Okay, so J will take care of SS, I think. So where J is an ideal of here, ideal vanishing. So you take the curve, N is down, in the opposite of the ordinary locus. So for n equals 1, this difference is SS. You remember these supersingular points. So J is exactly related with SS. And F, I will just write, is a coherent sheaf of Xn extending this sheaf. So then this is very involved, it's kind of involved, because this sheaf is a little bit weird in the sense that this leaf always just lived here. Because you remember the construction was, everything was over ordinary locus. It's not living over all the curve. So because that, you need to choose to make some choices and became a little bit involved. You need to introduce this stuff, okay? But that makes sense to that. But you can just have the flavor that is very similar to the construction made by Héctor and looks okay. Okay, and that is the good model that we care about. Héctor will consider this one an H0, H0. Okay? Okay, finally, oh, great. Finally, so I give you the big chief. I give you the two models that we care about, which will be H1C and H0. Both will be our job that we want, this N and M on the statement of the last week. And finally, to perform the construction really, we need to cut these models. We don't care, we don't need, so we don't want to consider them because they are very huge. And our main goal today is just to consider the ordinary part, no? So we need to cut them. So we need operators over this cohomology. So just introduce two correspondence that will be,
That limit is this way?
Oh, let's think about it. So if JL is in JL plus 1, no? So it's a limit, no?
Yes.
No. No, maybe no. Is there, no?
No, Xn is inside Xn.
No, because it's an ideal, so it became smaller and smaller. Oh, that makes sense, no? I think
It's louder. Because it's the same thing that.
it's direct or that in your
It's the same thing as we did the last time. So this
You're
is
right.
the compact things. So you want to consider the compact cohomology. You compare with something that is compact, but you have to put zeros. But in a profile,
Yeah. So you think it's
Last time we had a debate.
but now it's confirmed that it's profile.
Okay.
oh yeah, because the debate was is it zeros or poles, but we want the compact support cohomology on the ordinary locus. So we need to put a lot of zeros in the super singular part. So that is the logic behind. So that means that it was projective limit.
What does it mean? I just say it's with the arrow.
Barrel in that direction or this direction? You think in this direction? Okay. Okay. One observation is that so this M is good, no? It's when you cut you quotient by the lambda by this finite set. So these shifts are reasonable the size, and you take the inverse limit of them. Okay, each one of them is profinite. Then you can each one of them you can use the theory explained by Luis, and also in this limit you can also explain the theory explained by Luis, and that was Héctor will use. So the theory explained by Luis at the beginning was just for finite rings, you remember? And we have this divide with only finite rings. But if you see how you take in limits, you can go to very, very big very models like lambda models, which are very big, okay? So you can just, okay. Now finally, 3.4 I think was, no? Yeah, and UP correspondence. Okay, so maybe I have 5 minutes, I think. So, 3 minutes. So let's 5 minutes. Maybe I will just concentrate in the construction of F, the Frobenius. Yeah, because you will mostly use that in your proof, no? Okay, so just in 5 minutes I can do it. Okay. Whew. Okay. F. This is F of Frobenius. Okay, how we construct this? Firstly, so I just want to remark that we have the operator TP is acting on the H0 and H1 of the XWK and the models we carry, TP. So here we are introducing two more operators or correspondences that will play a role that will be related with this TP that we care. This will be kind of tools to study the other one if you want. Okay. Okay. So we start with Frobenius. So Frobenius. So you take a map on the ordinary locus. Okay. Which is this map. So now I will forget the notation that I set up. Okay, so the points here were just elliptic curves plus a gamma 1 n structure. I say that we don't care about this, but in the construction of these two correspondence, this gamma 1 n structure plays a role. So just recall now. And what do? You need to associate another curve, and you will take the quotient by the canonical subgroup. You will take the canonical subgroup 1, and you need to consider some gamma 1 n structure attached to it. And this will be exactly the gamma 1 structure given by the quotient, no? Where is the gamma 1 n structure induced only the projection. Okay, so you have a gamma 1 n structure here, and then you just go to the quotient. Okay, I will not give the construction of this one. When you look at this, you will use a different gamma 1 n structure. Will be the kind of the dual of this one. Just wanted to remark that. Okay. This Frobenius. So here we had a discussion with Héctor now about why this is called Frobenius. And the thing is that mod P, and this is really Frobenius what you say, no? Kind of. Yeah. Okay, so the name Frobenius makes some sense. Makes sense. Okay. Okay, so this. So now we want some correspondence at the level of big chips. So we need to look at these steps, no? We need to follow these steps and go in here. But in fact, F extends to F, a new F, that go from the Igusa tower to the Igusa tower. Okay? So at the level of points here is the same. You just need the trivialization of this state model that you need to introduce a new trivialization. But because the construction is given by quotient, taking a quotient by the canonical subgroup, the trivialization is compatible and you can construct this. Okay. Okay, so you have that. Next step, you want to pass from here to here now. Okay? And that is called, they have done this. Have a name is. Yeah, so I think this is the Part 3, taking the pullback, you have a map between shifts. Is take the push forward, yeah. Pullback I'm saying here, no. Take the pullback of the structural shift over the USACH tower, and you have a map from here to this. Okay. So one observation here is that you have an action of ZP star here, you have an action of ZP star here, and in fact this is ZP equivariant by this action. Then finally you get taking, so you take tensoring this with lambda, then taking ZP star invariant, you get till here, and you get a map we will call F again, that go from the pullback of this big shift till the big shift itself. And that is a map of, so you get a map of shifts over XOR, which is this map. And this will be considered by Héctor. Okay, that is, okay, the construction of UP is very similar, modifying a little bit this gamma 1 structure and taking push forward instead of pull back. Okay? Okay, so that is I wanted to explain you. So now the Héctor will use all this machinery to say something. Okay.
Question? Comment?
I have a question, but it's probably stupid. I just don't know, like, why is this Frobenius model?
It's a good question, yeah. Yeah. So you need to think, what is the canonical subgroup mod P is the kernel of Frobenius.
Okay.
Then you're taking E time quotienting by the kernel of Frobenius. Yeah, so it's not very clear my answer.
I mean, each one is like UP. Yeah?
Mm.
So what is the kernel of Frobenius?
Okay.
UP. So it's kind of like that.
Yeah.
I mean, there's a lot of things to prove, and when you have to prove, first construct the Frobenius, then you have to show that it's an isogeny, and then. But I think that will be the first step, I guess. I mean, this is like an idea, maybe?
No, yeah, that's an idea that, but we have no precise answer, maybe. Yeah, that's, yeah. So I know that was a little bit involved, but it's normal. If you understand everything, that means that there is something weird, no? So it's normal that you see some stuff that is new, okay? For stuff that we look each semester, so it's normal that you don't understand. Okay? But if you had some feeling, which is good, that is important. That is, and you know that there exist these kind of constructions. Okay, that is okay. We stop a little bit and.
Let's think again. Okay, now we will continue with Héctor's talk that will be about the proof of the main theorem.
Okay, so I forgot my notes. Okay, so I will talk about the proof of what theorem. Okay, that's the first part. Oh, it's always good to know what theorem we want to prove. Yes, so let's just start with the statement. So theorem that is theorem 4.15 in the article. It won't fit in that part of the blackboard. Okay, let's maybe the first part. hopefully. So the theorem says the following: there exists, I think it's an endomorphism, an endo, okay. Sorry, Spanish put the adjectives. Locally finite, locally finite endomorphism F on H1, the compact support first cohomology of this p-adic completion of the modular curve. Yes. Omega K. Okay, I think this is right. Yes. So there will be, we will have to define an F, an endomorphism on this space. Okay, this is a profinite space over some this other ring, just lambda. And so that's the first thing. And the second thing, and this. So since this is locally finite, we can define this EF. Okay, this is abstract nonsense of X or W. And this module is a lambda module, how do you say this? Finite projective lambda module. Okay. Moreover, this module, okay, I think it's like this, yes, or K1 is isomorphic, and sorry, if we take the specialization with tensor by the specialization map, okay, I think we denote this like this. This is isomorphic to E PP H1 K. So
One observation, maybe the X is different in each.
yeah, true. So this is like a nice X, and there's another X. Okay, and this is for K less than -1. Yes. So let me think. Okay, everything. Okay, so we have this. Is the statement say we have this F that is locally finite on this profinite vector space. Furthermore, this projection, you know, what we call this EF, is a finite projected lambda module. And actually, if we put this, if we take the specialization to K, so maybe here, so here's a K, and this is the same K. There's two Ks, and these are the same ones. Okay, that should be maybe. So it's inside this tensor where this K appear. Okay. I mean, the idea, this is like the whole family of every possible weight, yes? And we just say, okay, pick one, and we pick one that is K. Okay, and this is actually the realization of the result that Daniel explained in his first talk. This is the statement in his talk. There was just some module, some things. Now we have explicit candidates for the theorem. Okay, the explicit candidates are these ones. Yeah? Okay. The compact support cohomology. And the second part of the theorem, I want to state it because there's something similar. There's something similar for UP. Okay, I mean this doesn't make any sense because we have to define UP, and this F, this is just a letter up to now, yes. But the idea that this is related with the Frobenius, and this will be related with the UP, the other operator that we didn't have time to define. So that's why I just write this. That the idea is that we can define a UP that satisfies something like this. Okay. Yeah. So the UP will work on not the first cohomology, the second, the zero one. Okay. And I think we don't need the compact support, for example. This is a remark I when I did when we talk in the mod P theory, there were always this condition, the weights were negative, and there was some similar theory for positive weight, but we have to change some things, and something similar changed here. And it was in the negative part that we used compact support. Okay, here is. So this is more involved. Yes. The compact support cohomology of current shift is involved. Yeah, as we just mentioned. Yes. So this is the theorem. So we will just, of course, the one that is stated is actually part one. So we want to prove this part. We will give the ideas. So we will do it like this and here. Okay. So the statement. So the second part is about the proof. Yeah. About the proof of the theorem. Yes, of course. So I can divide this proof in 4 parts. Okay. So I don't know if I probably will just see the first two ones, but maybe just mention. So the first part is like the setup. Okay, setup. So where we define. We say, okay, what we want to do, because these are very abstract objects. Yes, how we deal with them. So the second part is the construction. Yeah, the construction of F. Okay. Then we have local finiteness, and the last part should be EF and EDP. Yeah. So this is like the 4th step, I would say. So let's start with the first part. Okay. So the setup. This is quite long. Okay. So yeah. So we recall that this H1C compact support, or WKK is, so it was a long definition, yeah. But so this is constructed, yeah. I don't know, with, I think, is the preposition, or yeah, with this H1C XN or K-un modulo this Jacobson radical of the lambda. So and this is for every positive n. Yes. So this one is constructed from this one. So what we will do is actually concentrate on this part. Yes. This is just definition. So let's study this this vector space, this profinite vector space. So since we want to study this, we need to fix we fix the following. We fix the following. The following. So this is kind of similar thing that Daniel just discussed. So we take xn or, and this inside xn. As we mentioned, this is a key step to define the compact support cohomology. What else? We take f. So f underline, okay? I don't want to do fancy f, so I just put an underline. A current shift of xn such that if we restrict this to xn or, it's just k1 is the shift that we start with, this one, okay? So as we mentioned, this is the procedure to define compact support cohomology. We go into something that is compact, and from there we define we just choose some current cohomology, and in this way, and from this we can define this compact support cohomology. So the other thing is that we also put this. So this sheaf that is so this is a sheaf of xn such that the zero locus of these sheaves is actually equal to x. This is the same thing that we just mentioned. Daniel talks xn or. So this is the complement of xr in xn. Yeah. So this is just what Daniel actually mentioned. X. Yeah, this is an n. Okay. Yeah. So this I is an sheaf is the zero sheaf. I mean, the point, this is open. Yes, this is open. So the complement is closed, and so it should be defined by an ideal sheaf. Okay. Okay. And now there's. So this is. But as you see, we can, in this construction, we can choose any f that satisfies something like that. No. We have free choice for that. I mean, one of the result is that the cohomology doesn't depend on all the choices. Okay. But this is a result on cohomology. So this is the thing. There's like a remark. We can choose f underline such that the following map is an isomorphism. So we take the ideal, or this sheaf, we take this tensor product, I mean this over OXN, and we go this in this way. I think this is right, yes. We can choose such, I mean this is like the definition of IF. So this is inside F. And we ask that this is an isomorphism. Isomorphism.
Is O, what is this?
Okay. Okay, OXN. No?
All these f's are the same.
Sorry. So this is the underline F. Yeah, so in this way, this is kind of saying that this ideal is non-torsion, because as you see, we are working over set. These are defined over aspect of C modulo, P to the n. Yeah. So this is not a field, yes, it's a ring. So there could be some torsion here. But using some abstract nonsense, we can actually reduce to this case, where this is an isomorphism. So this is like this. So why we do this, and this is like one of the first, this is a very useful thing because of the following. In this case, we have that if we push forward the shift K1 modulo n is isomorphic to the colimit. Okay, I know the colim is not the preferred version, but in this seminar, but okay. So it's so here's there's something I want to explain. So okay, we have this relation. So the left-hand side just means that okay, take the one that we have defined over x and or and just extend in a very nonsensical way to xn. So what is this? So we do this. So what this means with respect to this f that we choose, this f underline. So this means that this shift is actually is taking this as f but putting poles. Yeah. This is not so if you restrict this to with j, we get this one. But if we push forward like in a nonsensical way, we might put poles in our shifts. Okay. So that's why this is a minus L. So this is L, and this L is positive. Okay.
Colimits means.
So good question. But maybe before colimits, what this means? What is I minus LF? Okay. Because the ideal, I can just multiply the ideals. Yes, I cannot put the inverse. But the point is that this ideal is actually generated by one element, just because in some sense we said the last time that the complement of this one is a divisor. So it's just a collection of points. Yes. So these are just, and locally, if I have a collection of points, I just get 1 point. So this will be just defined by one equation. Okay. So that means that it's invertible. Okay. Okay, using some dictionaries. So actually, if we want to define this, this is just so this ideal is invertible. So it's like this. Okay. F. So this is the first thing, that this is defined by one equation. So it makes sense to invert this. You just invert the element that define this one locally. And now the question about the colimit. So the colimit is this limit. I don't know the name. Is this one. So
Directly.
I think okay, I don't know, but you say it's direct. But I mean, how I think this one, this is like unions. This limit is union of things. So this say that when I push forward this thing, I get poles but fixed poles. You know? I cannot have arbitrary big poles. You just get 1 pole and I don't know 5. Okay, and so this one, if I push forward, is a union of I just put some finite poles. Okay, the inverse limit could it's like you putting together a lot of infinite things. This is just you stop at some finite part. Okay, so this is the idea of, so that's why we do all this, just to say that the push forward of the shift that we start with is just put poles in the shift that we choose that extend that one. Okay, so it's kind of confusing, but the idea is just relate everything with F. Okay, very, very good. Okay, so this was the first part of the setup. Now the second part is the following. So we can define this. I don't know, this like covers x0. How can I call this one 0, the level p? Yeah, we introduced these ones. So we have this 0, this level p thing living over xn. P2, yes. So maybe we'll talk a little bit more about this later, but okay. So we just recall that we have this situation, and so we have this. So here's like a remark. P, the push back of these ideals. This is something that probably. So I push back these ideals that lives here, okay, are shift, are locally principal. So this is kind of the same as being a divisor. Principal shifts. Locally that define the same how do you say this? The same close sub. So these are, as I said, these are the ideal defining the complement of the XOR n inside xn, and we push this back, and for some studying this p1 and p2, one can say that actually the push back of this one also define the same. Okay, I mean this one and this one define the same closed subset of xn. Okay, x. Sadly, I cannot really comment this too much. Maybe with some picture we can see a little bit why this is true.
Off.
Yeah, off. Sorry. Maybe we'll do some picture and try to explain this. But for the moment, just say this. So since this is true, I mean, these are locally principal, so this implies that there's this following relation. So this is the remark. We have, I don't know. We have the following. We have that there exists R and S positive integers such that pi1 star, yeah, R is inside p2 star S. Now, thanks to this remark, we have this, that there exists R and S such that this is happening. You know, I mean, the idea is that if you have two ideals that define the same closed space, subset, then this implies that in some good situation like this one, that the ideals are like a power of each other. Yes, yeah. I know. I mean, this, if you want a very easy thing, is like V. If I define, I don't know, take the polynomial ring, okay. Vt, the one that the ideal generated by D is equal to the one that is defined by the power of T. The zero locus of the ideal of the power of T is the same as the one with no powers. Yeah, and this is the same situation, something like this. Yeah. These are defined by some power or something. Okay, so this is the idea. Okay, I think, and this should be this is the setup. Okay, we define these things. and we have this property on the pushback of this. So now let me start with the construction. So construction. The construction of F. Yeah, I think this should be okay. So the first thing is, I want to recall, I didn't really introduce this in my talk. I should have. It was part of the proof. Okay. If we go deeper in the proof, we will have encountered this, but okay. So the first thing is that on this part, on level P, we have the following decomposition. Pn or F, this is something called the Frobenius part, is the union is the disjoint union. Okay, let me put on the other part, by the way, and or V. So this is something called Frobenius, and this is Versibum. Okay, this is equal to or. Yeah. So what are these parts? So this one is said to parameterize. So these are the things living here that parameterize. How do I say? Parameterize Frobenius isogeny. I don't have time to say what this means, but Frobenius isogeny. In some sense, isogeny.
Maybe you could say there that you have a pair, no? A elliptic curve plus a level structure at P.
Yeah.
The group C, which is the structure at P, is equal to the canonical subgroup in the F.
Yeah.
This F here is the Frobenius, but the F in the theorem is different.
No. Should be.
Okay.
We will use this one to. That's why I'm putting this. Yeah. We'll use the F Frobenius to define the F in the theorem. Yeah, that's.
That is pretty clear if you consider the points in X0P as a pairs E and a subgroup of order P, which is the structure at P. And the condition to be there is that C, this subgroup, is equal to H1 canonical.
Yeah.
And you remember the Frobenius was constructed using that. So
Yeah. So that's the idea. Yeah.
transparent from that point of view.
Yeah. So maybe an object here is something like E and the HN canon.
H1. No?
H1. Okay. We are very in N, yes?
No, but the
Okay.
level at P is just P, not X0, it's
No.
not P. So that means you have a subgroup of the P torsion of it.
Okay, yes, true. So these are the elements in this thing that this group is actually, it's isomorphic to that one. Okay? And there's something similar here. There's another subgroup, but for the Versibum part.
The subgroup such that is not the canonical.
Yeah. Okay.
I think I'm not precise.
But okay. Oops. Actually, a little discussion about that will happen now, I think. There will be, I will write some consequence of what we just discussed, maybe of this one. Okay, but maybe just to make a little picture, I think this will look like this. Okay, so X0P, as I think this is a draw from, I hope I take this from Daniel. So this is X0P, and here we have, okay, N if you want. And so as you see, this is smooth, and this is not smooth. And where it's not smooth is like in these intersections. Yeah. So what is this? So I should have used another color. So the green one is the, you can think this as a picture. Yes, one irreducible component is F, and the other one is the version. Okay? And the other thing is that, here is the whole thing, but here we're considering the ordinary part. So what we do in the ordinary part, we remove these singularities. So, okay? So if we remove this will like disjoint and will form this disjoint union. Okay, so what do you want to say?
Nothing.
Okay.
No, exactly that you don't put orth, but now.
So with the circles are the orth. Yeah? So that's a picture. Actually, this picture will also. So here we have the P1 and P2, and this behaves in different manner in this, decomposition. Okay, so we have this. So in some sense, here we haven't used that these are like Frobenius or something like that. Yes? But I think now we will use the. We have to choose one of them. So we observe. I think it's so that the graph. I will try to explain this. That the graph, or maybe of the Frobenius morphism, orth here. So this is a function in this way, okay? And I think this is defined as Daniel just explained last time. So the graph is, and this is something related to what we just discussed, is x0 p orth f. Well, it's isomorphic. It's iso to this. Okay. So what this means, that this is the graph. I mean, I don't want to define all the things. Maybe let me just put the consequence of this. So if I write these ones, so I take x, p, or f, and I consider the projections, okay? P1 and P2, and x or xn or. So what it is saying is the following, that P1, I mean all this, that P1 is actually an isomorphism. Okay, this is the first claim, that P is an isomorphism, then I can do an arrow in the other direction, and if I do this composition, the inverse of P1 and P2, this we are going to obtain F. Yeah. So we can relate the Frobenius with this P2 and P1 and P2 that are kind of, if we recall the correspondence talk, the idea is that the correspondence are like a generalization of functions. Yeah? But in this case, this generalization of function was actually a function. Okay. Okay, so this is kind of the same thing. Okay. Thanks to this, we can do the following. So we are still discussing about the construction. Yeah? Thanks to this, so we are relating. We just translating things from the function. This is a function, and we are related it with a correspondence. Yeah. And so we have this. I don't know, following this, we can reinterpret interpret, I guess, these two things. So we have the Frobenius, xn odd, and this is the one that defines Daniel, and also this one that we also call F. Okay, so be careful. Is the sheaves. So this K1. So we have this function, and we have a morphism of sheaves. And thanks to what this graph condition, this can be reinterpreted as the following, as a correspondence in the language that we define in the talk about correspondence, as a correspondence between P2 star omega K1 P1 exclamation, sorry, key. So this one K1 so this one give me pi P2 and P1, and this F can be reinterpreted like this. Okay.
Or what? Over the X.
Ah, yeah. So over X or N 0 P N 0. I mean the idea of the correspondence is live in this space, yes. So wait. So because up to now maybe it was defined over in this part, in the Frobenius part. So as a correspondence like this, that is, we support. Sorry. On, or maybe it's more emphatic, trivial on X0P or V. So using this abstract nonsense of relating graph with correspondence will just give us a function sheaf on the X0, P or F. Yeah, but this is a disjunct union. So I can extend this by just saying, okay, just say 0 in that other part, and we can extend to the whole 0, X, 0, P and OR. Okay. So if you want this. Okay. Trivial on, yeah, I think it's fine. Maybe I will write this. Okay. So we have this reinterpretation. Okay, this is just a reinterpretation. Okay, so what we win with this? So this is a reinterpretation of a fact living inside X ORT, okay? And we want something. If we want to define this F, we should consider the whole Xn. So what we do is we take this construction. So now we push forward this construction. Here maybe it's a little bit not very precise, but let me just tell you the ideas. Now we push forward this one, and so we push. We then obtain the following. I will explain a little with ideas why this is true, but so we take a morphism between colimits, a morphism of sheaves of this way. So let me just, so I don't make any mistakes, minus LF underline colim L P1 minus. So if we push forward this condition to xn, so this is over xn orth, yes? And we push forward this to xn, what will happen? So as this actually was in this part of the blackboard, this one push forward is related with the f that was extending this one, but with poles. So that's why disappeared this column of poles, yeah? Because we're just pushing forward things. So when we push forward things without carrying anything, we might put poles in our constructions. So that's why we have this column thing with negatives. So this is just something, because we start with something just defining x and r.
Where should you start?
P, yeah, sorry. So actually, this implies the following. Okay, we have obtained this thing. Thus, we obtain the following map. Okay, that is, we can obtain P2 F underline 2 P1 I minus C F for some C is a natural integer. But it's a positive integer, sorry. So this is like putting together a bunch of things. So I just like taking a component of this one, and this is actually the same thing I was telling you. Since this one is defined over xn orth, if we push forward this, we can define this to xn, the whole xn, but we pay the price with the poles. Okay. So this is the idea. Okay, we pay the price with the poles, but in order to define something for the compact support thing, we have to, this is the contrary, yes, we have to put zeros. Yeah.
Confused. All this working over xn now.
So this is over xn, yes. It is over xn, and this one was over, I just xn orth. Sorry, this is not really. It's 0 p orth, and this is 0 p n. No. So as I say, the price of with the super indices is paid by poles. Okay. So in some sense, so we start with Frobenius, and the Frobenius, all these constructions start with this one, with just the Frobenius. And this Frobenius pull poles. Possibly, okay? Maybe doesn't. So we have this. This is finally, or yeah. But now we recall this inclusion. Thanks to the fact that P1 star Y is R, P2 S. So recall that in the setup we note that the inverse image of this one are the same. We have this relation, yeah. We can deduce or define the following. So we start with P2, and we take a power of LR, I think, yeah, R, F underline, and this will land, just following the construction, to P1 star, no, exclamation, sorry, I minus C plus SL times okay, if we send to this relation, we take multiple of this one and we land in this way, in the other side. Okay, just comparing these two shifts, because this was without the the ideal. So we have to say what happened in the ideal. This is telling me what is happening with ideals, and then we just put it together with this function. So let me say this is for L greater than equal to 0. Okay, good. So, and this is the one that we want to use to define the f of the theorem. But so let me explain you why. Because if you see, if I put L bigger, so the problem here is that in that part, for example, is that this is negative. But if we put L sufficiently large, this will start to be positive because C, S, and R are fixed. Okay. So if the only thing that is varying here is L. So if we put L bigger, bigger, and bigger, this will become an idea, a positive. I mean, this map will start to put zeros. Okay. So we pay the price, but it was a finite price, and we have infinite amount of money. Then we win, I guess. So we now take the limit to define f from x1 c xn or probably okay, this correspondence give me a morphism between the cohomologies, and putting all this together, because this is for every L, we can form this F. This is for every n. So moreover, because we're taking this for every n, we can put all these constructions together and form the big F that we wanted in the theorem. So that will be the construction. Okay, this implies f on the whole thing, just x in the port WK1 this was for every n. Okay. Sorry about the mess, but okay. Okay. I mean, to define something here, we just need to define in every, as I mentioned in the beginning. So, I think, I don't know how much time I have. Can you help me with that? Because we start around, I think it should be fine, yes? So I think I will leave it here, and I missed 2 parts, but okay. I think this is, maybe at least this could justify the notation F for the map, yes, because it was constructed from F. So yeah. Okay.
Yeah, you have 10 minutes.
Ah, okay, I have 10 minutes.
Yeah.
Okay, I guess. Okay, if you want, I have 10 minutes. So let me talk a little bit, so to finish, let me talk a little bit about the local finiteness. But anything is, okay. So we construct this F. We know that it's related with the Frobenius thing, okay, that Daniel defined. And now we have to prove that this is locally finite. Yeah? So the the 10 minutes part local finiteness. So as we have been discussing, we actually to work with this, we work in every n. Yeah, in every piece we start defining thing. Okay, that's the idea of this. I mean, that's the definition. Yeah? So since we want to work with every n, we will do some kind of induction. So as n induction, let n be equal to 1. So we start with the base case. So we want to study this morphism, but with n equal to 1. Okay. So what happened in n equal to 1? So okay, maybe there's things that I didn't mention, but for example, so these are morphism of lambda modulo n. No? These are lambda modulo n modules. So we need to, I want to study this, so I will study this ring. Okay? So since n is equal to 1, I just put lambda mod m. Okay, this is by definition the fp star. I want to study local finiteness. And to do that, I will study this ring. It's clear this is isomorphic. Yeah. This is the definition, as I say. Yeah. But in this case, so what is this? What is this fp bracket finite group? Okay. So actually, this is also isomorphic to fp. Okay. Before doing the isomorphism, I will just say this is equal to f, or maybe behind, no, like this. This is equal to, I mean, to this, where C is a generator of fp star. We know that the unit, I mean, this is fp, so okay, but this is not so clear, I think, even for p. This is a cyclic group, so it's generated by one element. Okay, with this choice of finite element, we can see that this is actually isomorphic to p minus 1 copies of fp. Yeah, so let me just say L mod L k mod p minus 1. So what you do, okay, this is isomorphic, and furthermore, I can, so this is true, there's a projection, yes? So what are the projections? We take p f generated by C, and we want to learn in fp, okay? So what we do, we take this generator, and we take the power to k. Yeah, and k is here, yes? You know, power is, this power is, will repeat after p minus 1, yes? So this isomorphism is realizing, is putting together all these maps, okay? And as you can see, this is kind of similar of this specialization map. If I consider this map from here to here, this is the specialization map that we find, but the specialization mod p. Okay. So this have the following consequence. So okay, I have lambda n. This is isomorphic to these copies L k mod p minus 1, and this, so as I say, this vector space, I mean this ring acts on this vector space. So I mean, sorry, acts, at least actually acts functorially, because this shifts, there's an action of this lambda mod m on these shifts, in this one, in this shift, okay? So there's an action here just by construction, K on modulo M. Okay, this ring up here. But thanks to this decomposition, there's also a decomposition with respect to this one. And actually one can choose in the following way. This is equal to K minus P plus 2 WK. Okay, this is probably an isomorphism. Since to this is the composition, we can write this using the specialization map that Daniel defined. Yes. Yeah. If you track down all these maps and what all this means, we get WK. I mean, we are using this, yes? That WK un tensor K lambda K set P, this was isomorphic to WK. Yeah. And if you further tensor this by the, I mean, for mod P, you get this isomorphism. Okay? In the projection are also explicit. So, anyways, so thanks to this one, we have the following, the composition of vectors, of profinite vector space. So, I think even, okay. I mean, using this, using a star, okay, we have the following. We have that H1C X or 1, I think, yes. This is actually isomorphic to 0 K minus Hort, I think, yes. Okay, in some sense, homology is additive. So, since we have copies of W, this is true. Okay.
That's X1 or?
Sorry. Yeah, sorry. I already talked too much, so maybe. Or. And this is compact support. So we have this isomorphism of, I mean, FP vector space, profinite vector space, pro vector space, professional vector space. So we have this isomorphism. So I mean, as I said, I want to prove locally finiteness for each of these ones. So we're studying for n equal to 1. So let's check why this is. With this, we can now check that this is locally finite, at least for n equal to 1. And the idea is the following. Here we have this f that we just construct. Yes. Now, if you follow what this f means in the bottom part of the isomorphism, one can check that this actually acts as a TP, as the correspondent we define. I think I define. No, this is one. Yeah, I defined this one. Just the TP, the correspondent defined in the previous talks. Okay. So thanks that this isomorphism transfer this f in this TP for every piece, we can show that this is locally finite because we know that these ones are locally finite. I mean, TP locally finite. Okay. And this is the result that I state when we state in the second talk. So this, using the previous talk, we can prove that this f that we construct is locally finite. Yeah. Yeah. So to prove this, for every n, we use some kind of induction, but I think this should be enough. This. I don't have much time, so let me finish here.